Hello everybody, lesson second. Topic is basic principles that include material structures and properties. Basic principles include material structures and properties and include the following subtopics: bonding and structures, dislocations, imperfections, plastic flow and strengthening mechanisms in metals, mechanical properties of material, microstructure and phase transformations in alloys, thermal properties of material. And for structure, we will understand what is the shear force and we will try complete a bending moment diagrams and understand what is this. So, bonding and structure. The idea that matter is made up of small, discrete particles is a very old one. Such a scheme was described by Democritus over 2000 years ago. Now we understand fundamentals and the structure of the atom. The modern concept of the atom was put forward by the English chemist John Dalton in 1800s. He shown atoms as small, indivisible particles, with the atom being the smallest quantity of an element that retains the properties of that element. We now know that atoms are not indivisible, but they consist of smaller subatomic particles, protons, neutrons, and electrons. Indeed, modern research in high-energy physics has shown that these particles can be broken down even future, but for our purposes an atom is most easily visualized as a nucleus surrounded by orbiting electrons. The nucleus contains most of the mass of the atom and consists of neutrons, large electrically neutral particles, and protons, large positively charged particles. The orbiting electrons are negatively charged and are tiny compared to the nuclear particles. The number of protons in the nucleus defines which element it is, and this number is called the atomic number Z. Table shows the relative mass and the charge of these three types of particles. For example, neutron's mass is 1.840, for protons mass is 1.836, and electrons mass is 1, and charge 0, plus 1 and minus 1. atoms is most easily visualized as a nucleus surrounded by orbiting electrons. The nucleus contains most of the mass of the atom and consists of neutrons, large electrically neutral particles, and protons, large positively charged particles. The periodic table. In 1869, the Russian chemist Dmitry Mendeleev first noted that the chemical elements have a periodicity of properties. He had tried to organize the chemical elements according to their increasing atomic weights. The modern periodic table of the elements is shown in figure. And is based upon Mendeleev's idea. It's organized by atomic number Z and not by atomic weight. As we move from left to right along a row or period, the properties of the elements gradually change. The last element in each row is chemically inert. So helium, neon, argon, krypton, xenon, radon. These are the inert gases. Those to the immediate left are the very reactive halogens. Fluorine, chlorine, bromine, iodine, astatine. Their reactivity or inertness results from their other electronic structures, as we shall see later. Therefore, the elements in any column called groups tend to possess similar chemical properties. The periodic table has enormous significance in understanding the chemical behavior of the elements, because it's rooted in their atomic numbers and therefore in their electronic structures. At this point, it is appropriate to point out that of the 100 or more elements in the periodic table, 3/4 are metals. Some of these, such as the rare earth metals, are found in nature in tiny amounts. In this modern age of electronic goods, some of these metals have become of great technological importance despite being used in tiny amounts. The volatile production of many of these metals is often only a few hundred tons in total. Bonding. We have looked briefly at the properties of atoms, but in practice our materials are made up of assemblies of atoms arranged in a myriad different ways. And we must now examine the various ways in which they can be bonded together. We shall see that it's the order electronic structure of the atoms that is responsible for the bonding, and not the nuclear cores. We shall also see that it's the qualities of these bonds that determine the properties of our materials. By properties, we mean principally the mechanical, thermal, and electronical properties of material. The bond types can vary widely in their strengths. The energy required to separate two bonded atoms is the bond energy. And this controls not only mechanical strengths, but also other properties such as melting temperature. An element or compound with a high bond strength will be more difficult to melt. That is, it will tend to have a higher melting temperature. It will also have a higher value of stiffness, Young's modulus of elasticity. Before we look in more detail at the various kinds of chemical bonding that are commonly found, it will be profitable to consider the cohesive force that hold atoms together and the binding energies involved. This consideration applied to the force of attraction between any pairs of atoms or molecules, be they in the gaseous, liquid, or solid states. In the next lecture, we shall consider thermal properties, but it's worth pointing out here that heat is atoms and molecules in motion. In solids, the atoms or molecules vibrate or wriggle about a mean position. In liquids, they move randomly around inside the liquid, colliding with each other from time to time. In gases, the atoms and molecules move with greater speed and move around randomly within whatever space is available to them. In any group of atoms or molecules, be they gas, liquid, or solid, there will be short-range force of attraction operating. That can be represented by curve 1 in this figure. There will also be strong short-range forces of repulsion that operate to resist compression when the atoms or molecules come into close proximity, and these are represented by curve 2. If these curves force are added, we obtain a a resultant force curve 3. Curve 4 shows that the system has minimum energy with the zero force spacing and will therefore be in equilibrium. So we would expect to see materials having high strengths also being difficult to melt, high melting temperatures, and having high stiffness values. In fact, there isn't such a link between these properties, and this is illustrated in this table. And here you can understand properties for diamond, a covalently bonded solid, and 6 metals, and from it we can see that ionic and metallic bonding can give rise to strong bonds. The bonding mechanisms all involve electron donation from one atom to another, or electron sharing in some form, or electrostatic attraction brought about by electron gain or loss. There are a number of primary bond types, the most common being ionic, covalent, and metallic. Secondary bonds include van der Waals and hydrogen bonds, which we shall now examine in turn. So here you can see a value of strengths of diamond, steel, iron, aluminium, lead, etc. For example, steel have strengths, yield strengths 400 megapascal and stiffness 200 gigapascal. And also you can see a melting softening temperature of each metal. About crystal structures. Solid materials can be classified according to the regularity or otherwise with which the atoms and ions are arranged relative to one another. Crystal structures are highly ordered. The state is characterized by a regular, periodic three-dimensional array of atoms, ions, or molecules, and these crystalline solids have properties that result from this high degree of internal order. Non-crystalline structures, on the other hand, are those without such long-range atomic order. Such materials are variously described as amorphous, glassy, or vitreous, and these terms are usually used synonymously. Metals are very important class of materials, and one of these characteristics is that they are crystalline. That is, the atoms are arranged in very regular arrays. metals therefore have some of the most highly ordered structures of all materials. Most of the metals correspond to one of the three simplest arrangements shown in figure. These three common arrangements are body-centered cubic, face-centered cubic, and hexagonal close packed. So, body-centered cubic, face-centered cubic, and hexagonal close packed. Body-centered cubic, this crystal structure type is found among some common metal, such as ferritic steel, pure iron, chromium, tungsten, etc. We can characterize the various crystal forms by their atomic packing factor. Atomic packing factor you can find like volume of atoms in a unit cell divided by total volume of unit cell. Face-centered cubic. This is the structure found in some of the common engineering metals, such as austenitic steel, aluminium, copper, gold, silver, nickel, etc. With face-centered cubic metals, the atomic packing factor is 0.74. This means that 74% of the unit cell volume is taken up by the constituent atoms. We can see from the atomic packing factor figure that face-centered cubic metal are more close packed than body central cubic. And hexagonal close packed. This is the third common structure type. And the common metals conforming to this type include zinc, magnesium, cobalt, and cadmium. The atomic packing factor for hexagonal close packed is 0.74. So it's a truly close packed structure.